In this part of the lesson, I'm going to talk about adding and subtracting fractions. I'm going to start with the easy problem, adding and subtracting fractions with the same or common denominator. We'll spend most of our time thinking about how to add and subtract fractions with different denominators. In the context of this discussion, we'll talk about the least common multiple. And finally, at the end, I'm going to briefly discuss some shortcuts we use when performing fraction arithmetic. So let's start with adding and subtracting fractions with a common denominator. Here's a simple problem, 3/7 plus 2/7. I'm going to draw a fraction bar divided into 7 equal parts. I represent 3/7 by shading in 3 of the parts. I can add 2/7 and altogether I have 5/7. So what I did here for arithmetic is I just added 3 plus 2. So writing this out, 3/7 plus 2/7, we add the numerators and write the result over the common denominator. Let's look at a subtraction example. 6/7 minus 4/7. Same fraction bar, I'm going to start with 6/7 shaded in. I'm going to take away 4 of them. I'm left with 2. So I just did 6 minus 4 equals 2. But when I write out my fraction problem, I still have that denominator of 7. I've subtracted the numerators, wrote the result over the common denominator, and ended up with 2/7. So our strategy, when adding and subtracting fractions with the same denominator, we add or subtract the numerators and then write the result over the common denominator. So let's just work a couple more examples. Let's find the sum of 7/11 and 6/11. Of 7/11 plus 6/11, our strategy tells us to add the numerators, write the result over the common denominator. So we have 13/11. 13/11 is an improper fraction. The numerator is greater than or equal to the denominator. I could, if I want, write this as a mixed number. Let me show you a picture of that. What I have here is our problem. In the first row, we have 7/11 shaded in. In the second row, we have our 6/11. And if you count the shaded boxes, you'll get the 13/11 we just found without any pictures. But what I'm going to do here is I'm going to take some of these shaded boxes and kind of fill in the open boxes in my first fraction bar. What I'm left with is one whole fraction bar and 2/11 left over. So I can write my answer here as 1 plus 2/11 as a mixed number. Let's do a subtraction problem. 13/8 minus 7/8, we're going to subtract the numerators. 13 minus 7 over 8, that leaves us 6/8. Now when I factor the numerator and denominator, I see that I have a factor of 2 common to the numerator and denominator, which is just 2/2 is just 1, so this reduces to 3/4. One last example here. We want to find the sum of 1 and 4/5. Well, I don't see a common denominator here. But I can write 1 as 5/5. Add the numerators and write the result over the common denominator. So 1 plus 4/5 is 9/5. Now if I wrote this as a mixed number, I get something that looks very similar to what I started with. One of the things about this notation that we use for mixed numbers is this means addition, even though there's no addition sign here. When we write this, we mean 1 plus 4/5. This is not multiplication, it's addition. 1 plus 4/5 is 9/5, which we typically write as 1 with a 4/5 next to it, even though this means addition. Unusual to not have an addition sign there. So now let's look at the problem of adding and subtracting fractions with different denominators. So the general strategy will be to rewrite the sum or difference as the sum or difference of fractions with a common denominator, because that fraction arithmetic is very easy. Now we're going to start with a very simple example here, 1/2 plus 1/4. You probably know the answer already, but I wanted to get to the underlying concepts here with some pictures. So here's a fraction bar divided into 2 equal pieces. Here's 1/2 of that fraction bar. We need to add to this 1/4. Well, it's very easy to get quarters out of this fraction bar. We just divide each half in half again. So one of the things we notice right here is that 1/2 is the same as 2/4. Now when we add 1/4, we're left with 3/4. So we can write 1/2 plus 1/4 is the same as 2/4 plus 1/4. Now we have the common denominators. We add the numerators and write the result over the common denominator. Let's look at another example. Let's talk about the lowest common denominator. The common denominator 4, used in the previous example, is called the lowest common denominator. The number 4 is the least common multiple of 2 and 4. Let's talk about that a little bit. Here are some multiples of 2, here are some multiples of 4, and we can see that 4 is the smallest of all these multiples that they share. The least common multiple of 2 or more numbers is the smallest number that each divides into evenly. The least common multiple of 2 or more numbers is often abbreviated as LCM. The lowest common denominator of 2 or more fractions is the least common multiple of all the denominators. The lowest common denominator of 2 or more fractions is often abbreviated as LCD. Let's look at another example here. What we're looking for is the least common multiple of 3 and 4 to use as the common denominator. We're going to draw some fraction bars again. Here's a fraction bar divided into thirds for our fraction 2/3. Here's a fraction bar divided into quarters. If I try to put these fraction bars together, the way we put together the fraction bars for halves and quarters in the previous example, I don't get a legitimate fraction bar. I do not have a fraction bar divided into equal pieces. So I have to think of something else. What if I take my fraction bar and divide it into 4 equal bits horizontally rather than vertically? Now when I put my 2 fraction bars together, I have a legitimate fraction bar divided into 12 equal parts. If we think about it a moment, we see that 12 is a multiple of 3, it's a multiple of 4, and in fact it's the least common multiple of 3 and 4. So let's write out our work here. One of the things we notice is that 2/3 is the same as 8/12. So 2/3 is the same as 8/12. We also see that 1/4 is the same as 3/12. Now how can I get 8/12 from 2/3? Well, I can multiply 2/3 by 1 in the form of 4/4. Multiply the numerators, multiply the denominators. 2/3 times 4/4 is 8/12. 1/4 I can multiply by 1 in the form of 3/3. That's how I get 3/12. So when I'm writing out the sum here, what I have is 2/3 plus 1/4. That's the same as 8/12 plus 3/12. We add the numerators, write the result over a common denominator. So 2/3 plus 1/4 is 11/12. Let's look at another example. Now we're going to add 1/6 and 3/4. Going to start with a fraction bar divided into 6 equal parts and a fraction bar divided into 4 equal parts. When I try to put them together, I have the same problem we had in the last example. I don't get a legitimate fraction bar. Well, I'm going to do what I did last time. I'm going to divide my second fraction bar representing quarters into 4 equal parts, but divide it up horizontally. Now I get a perfectly good fraction bar with 24 equal parts. But let's think about multiples of 6 and 4. Let's think about multiples of 6. 6, 12. Well, 12 is a multiple of 4 too. In fact, 12 is the least common multiple of 6 and 4, and that's not what we got from our fraction bars. So let's think a little bit more about what's happening here. I'm going to go back to the original picture. One of the things that 6 and 4 share is a factor of 2. In fact, if you look at my fraction bar for 6, I could divide it into half first and divide each half into thirds to get my fraction bar representing 6. I'm going to make a fraction bar representing fourths by dividing it in half first, and then I'm going to divide it in each half in half vertically. So now I have 4 equal parts. When I put this together, the two lines representing 1/2 line up, and now I have 12 equal parts. I have a number representing the least common multiple of 6 and 4. So what do I have here? Well, 1/6 is 2/12. 3/4 is 3, 6, 9/12. So let's write out the sum. 1/6 plus 3/4. From looking at our fraction bar, we see that's the same as 2/12 plus 9/12. Adding the numerators, that's 11/12. Just a coincidence that we got the same answer in this problem as in the previous problem. Now what we're working at here is a strategy for coming up with the least common multiple. So I want to discuss the last 3 examples a little bit. So let's talk about what we saw. In the first example, 4 is a multiple of 2, and it was also the lowest common denominator. In that problem, our common denominator was 4. In the second example, the two denominators share no common factors except 1. 3 and 4 are called relatively prime. The lowest common denominator in this case was the product of the two denominators. We used 12. Finally, in the third example, 6 is not a multiple of 4, but 6 and 4 share a common factor of 2, which is why 12 and not 24 was the least common multiple we used for 6 and 4. So now let's kind of put together some of these ideas to see if we can come up with the least common multiple of 15 and 6, which is what we're going to need to find this difference. So we want to think about factors. And so what I'm going to do is write out the prime factors of each denominator. So 15, I know, is 3 times 5. 3 and 5 are prime numbers. And 6 is 3 times 2. So I see that 15 and 6 share a factor of 3. So I'm going to take 2 fraction bars and divide them into thirds first. Now my fraction bar in the bottom I'm going to use for the 6th. I'm going to take each third and divide it into half. Now for my fraction bar representing 15ths, I'm going to take each third and divide it into fifths, and I'm going to do the division vertically rather than horizontally. When I put these 2 fraction bars together, I get a fraction bar with 30 equal parts. If we think about it, 30 is indeed the least common multiple of 6 and 15. So now I can find the difference. So what I'm going to write here is I'm going to write out some intermediary steps. 11/15 minus 1/6. I know that I'm going for a common denominator of 30. Now the only thing I can legitimately do here is multiply each term in this subtraction problem by 1. Now I'm going to write 1 in the form of 2 over 2 and multiply that form of 1 by 11/15 because 15 times 2 is 30. I'm going to multiply 1/6 by 5 over 5 because 6 times 5 is 30. I know that the common denominator I'm going to use in this case is 30. Now I also want to point something out here before I do the arithmetic. This 2 was the leftover factor from 6 that we didn't use. Remember, 6 and 15 shared a factor of 3. This 2 was that extra factor of 6. 15 was 3 times 5. This 5 was that extra factor of 5. So we used the 2 and 5 in addition to the 3 that the two denominators shared as a factor. Let me just do the arithmetic now. So doing the multiplication, I have 22 thirtieths minus 5 thirtieths, subtracting the numerators, writing the result over the common denominator, I end up with a result of 17 thirtieths. So I want to talk a little bit more about least common multiple. Here's a strategy for finding the least common multiple of 2 or more numbers. It's going to sound like a mouthful, but when we do some examples, you'll see it's quite easy. We're going to start by finding the prime factorization of each number. Then we're going to list all primes that occur in one or more factorizations. For each prime factor, we need to identify the maximum number of times it occurs in any one factorization. This is going to be the number of occurrences in the least common multiple. Well, let's do that. Let's find the least common multiple of 30 and 45. We're going to start by writing the prime factorizations. So what are the prime factors of 30? Well, I know 30, for example, is 5 times 6. 5 is prime, but 6 is not. So I could factor 6 into 2 times 3. 5, 2, and 3 are all prime. Let's do the same thing with 45. I know that 45 is 5 times 9. 9 can be factored further into 3 times 3. So 30 contains factors of 5, 2, and 3, and 45 contains factors of 5, 3, and 3. Both numbers share a factor of 3 and a factor of 5. Now let's find the least common multiple of 30 and 45. The first thing we want to do is list the primes that occur in each of the factorizations. So I have 2, I have a 3, and I have a 5. Now I have to look at the number of occurrences. Well, in the first factorization, I just have 1, 2, 1, 3, 1, 5. But in the second factorization, I have 2 factors of 3. I'm going to need 2 factors of 3 in the least common multiple. So I'm just going to add in one more factor of 3. Now when I do this arithmetic, let's see, I have 2 times 3, which is 6. 6 times 5 is 30. 30 times 3 is 90. So the least common multiple of 30 and 45 is 90. Now you might be thinking, why do we have to go through so much work? Well, you know what? We really don't when we're working with some simple arithmetic. But when we're working with algebraic fractions, which you'll be doing later in algebra, you'll be using these strategies to find least common multiples of something called an algebraic expression. Now, let's finally summarize our strategy for adding or subtracting fractions with different denominators. The goal is to rewrite the problem so that the fractions have a common denominator. We want to find the least common multiple of all the denominators to use as this common denominator. How do we do this? We factor each denominator into prime factors. Multiply each fraction in the sum or difference by the appropriate form of 1 to determine the equivalent fraction with the common denominator. And this appropriate form of 1 is found by determining the prime factors needed to complete the common denominator. When we're done all that, we just add or subtract the equivalent fractions with the common denominator. So I'm going to work an example working out all the steps in excruciating detail so you can see how this works. So let's evaluate 5/12 minus 2/9. So what I'm going to do is keep track of my least common multiple that I'm going to use kind of down here. I'm going to do some scratch work. And so I'm going to factor 12 into its prime factors. 12 is 2 times 2 times 3. 9 factors into 3 times 3. So let's think about what we're going to use for a least common multiple. We need a factor of 2 and a factor of 3 because 2 and 3 are the primes occurring in the factorizations. Now we have 2 factors of 2 in our first factorization. We need 2 factors of 2 in the least common multiple. So I'm going to add in one more factor of 2 so that I have 2 factors of 2. Here, in this factorization, I have 2 factors of 3. Well, my least common multiple needs 2 factors of 3, and so far I've only put in 1. So I'm just going to add one more. So now that I have everything factored, now I want to think about the appropriate form of 1. Well, here's my least common multiple down at the bottom of the screen. Looking at the denominator of my first fraction, I see that I need one more factor of 3 in order to get the least common multiple that I'll be using for my denominator. So I'm going to multiply this first fraction by 1 in the form of 3 over 3. So I get that missing factor of 3. Looking at the second fraction, I see I'm missing the 2 factors of 2 in the least common multiple of the denominators. So I'm going to multiply the second fraction by 1 in the form of 2 times 2 over 2 times 2. Now I'm ready to go. I have 15. Let's see, what's my common denominator? 4 times 9 is 36. I have 15 minus 8 in my numerator, and that leaves me with 7 over 36. And if I was turning this paper in, I would just indicate that this is scratch work over here. Let's do another example. Here we're going to add 3 fractions. I'm going to start with 3/14 plus 1/10 plus 2/15. I'm just going to start by factoring the denominators. 14 factors into primes 2 times 7. 10 is 2 times 5. 15 is 3 times 5. So let's keep track of what I need in my least common multiple of the denominators. I need a factor of 2. I need a factor of 7. I need a factor of 5. And I need a factor of 3. Let's look at how many occurrences of these factors we have in each denominator. Only one factor of 2, one factor of 7. One factor of 2, one factor of 5. One factor of 3, one factor of 5. So I need no more than one occurrence of any of these factors. So here's my least common multiple of the denominators, which I'm going to use as the common denominator. Now I need to get there, build up all my fractions to have that common denominator. So I'm going to multiply the first fraction, 3/14, by 1 in the appropriate form. Well, what's missing? The 3 and the 5. In the second fraction, my denominator is missing the 3 and the 7. So I'm going to multiply the second fraction by 1 in the form of 3 times 7 over 3 times 7. Finally, in the last fraction, I'm missing a factor of 2 and a factor of 7. So now, just to double check my work before I move ahead, 2, 7, 3, 5. 2, 7, 3, 5. 2, 7, 3, 5. I've got the common denominator. Now it's time to do arithmetic. So my common denominator is going to be, let's see, I've got 2 times 5 is 10, 70, 210. In the numerator, I have 9 times 5, which is 45, plus 21, plus 8 times 7 is, 4 times 7 is 28. Adding the numerators, 45 plus 21 is 66, plus 28 is 94. And I'm going to leave that as an exercise for you to reduce that fraction. I'm going to finish up by talking about shortcuts. In this part of the lesson, and in the previous part of the lesson on multiplying and dividing fractions, we rewrote numerators and/or denominators as the product of prime factors. The following shortcut is useful when performing arithmetic problems, but the strategies we discussed in these lessons will be the only strategy to use when working with algebraic fractions. One of the reasons why we went into all this detail is to help get you ready for algebra. So let's just talk about the shortcut we can use when we're just doing plain arithmetic. So I'm going to start by writing out the fractions in my sum. I know I need the least common multiple of 4, 5, and 10 to use as my common denominator. Well, let's think about multiples of 10, the largest denominator. 10, that's not a multiple of 4 and 5. 20, oh, that's a multiple of 4, it's a multiple of 5, it's a multiple of 10, it's the least common multiple of the denominators. So that's going to be my common denominator. So I don't have to do any factorizations. I can think about this in my head because it's arithmetic. Now let's build up the fractions. In order to get a denominator of 20, I need to multiply 4 by 5 over 5. I need to multiply 2/5 by 4 over 4. And finally, I'll multiply 1/10 by 2 over 2. Now this step, there's really no shortcut here. Got to show what we're doing, how we're building our fractions to get the common denominator. The common denominator is 20. I'm adding the numerators 5 plus 8 plus 2. So I have 15 over 20. Now I can reduce this fraction in my head, most likely, without writing out the factorizations. I know that both 15 and 20 have a common factor of 5. What does that leave me? It leaves me 3/4. So here I didn't show all the factorizations, but I did show enough work to make it clear what the strategy was that I used to get 3/4 as the sum. That ends my part of the lesson. Now I'm going to turn it over to Steve, who's going to do some applications with you.
In this part of the lesson, we're going to work a few applied problems that just happen to involve fractional arithmetic. So let's work some application problems involving fractional arithmetic. Let's look at this problem. One day, Sandy left her house and drove 1 3/5 miles to the drugstore. She then drove 2 4/7 miles to the vet to pick up her dog. She drove directly home from the vet. The total distance Sandy drove was 6 miles. Here's our question. How far is it from the vet's office to Sandy's house? Let's pick out the key information from this problem and kind of summarize it so that we have a good working frame to develop our answer. We're told that the distance from Sandy's home to the drugstore is 1 3/5 miles, and that the distance from the drugstore to the vet is 2 4/7 miles. The other number that we were given in the problem is that the total distance that Sandy drove is 6 miles. And what we're trying to figure out is how far was it from the vet back to Sandy's house. Sometimes it helps people if they draw a little picture of the problem that they're trying to figure out. So Sandy here, she's starting at home. And the first thing she does is she drives to the drugstore. She does her business in the drugstore. She gets back in her car. She drives to the vet. She picks up her very happy dog, and they both go directly home. Now we know that the distance from the home to the drugstore is 1 3/5 miles. I can foresee in our future that we're probably going to have to do some adding and subtracting of these numbers, and it's much easier to add and subtract numbers involving fractions if you write the numbers as improper fractions than it is if you write the numbers as mixed numbers. So I'm going to go ahead and take that 1 3/5 and I'm going to change it to an improper fraction. Since 1 is 5/5, 1 3/5 is 5/5 and 3/5, and when you add 5/5 and 3/5, you get 8/5. So the distance from Sandy's home to the drugstore is 8/5 miles. The distance from the drugstore to the vet, let's see, we have 2 4/5 miles, 2 4/7 miles. 2 written as sevenths would be 14/7, because 14 divided by 7 is 2. 14/7 and 4/7, that's 18/7. So the distance from the drugstore to the vet is 18/7 miles. And the unknown is how far is it from the vet to Sandy's home. So I'll just put a question mark there. Now the other piece is that the distance all the way around this little triangular diagram I've drawn is 6 miles. So one strategy we could employ to find the unknown distance is we could add the distance from the home to the drugstore to the distance from the drugstore to the vet, and then we could subtract that total distance from our 6 miles. Now, when we perform these calculations, we don't really need to write our units down. This is something that a lot of math instructors don't do when they're performing calculations in applied problems. They don't write the units down. When you take your science class, they'll probably tell you to write the units down, but this is math class. So as long as your instructor's okay with it, you don't need to write down your units when performing your calculation. On the other hand, it is a good idea to write down a phrase or something that orients the reader and yourself to the purpose of the calculation that you're performing. And since you're writing a phrase down anyway, you might as well remind yourself and the reader that there are units attached to the numbers that you're calculating. The first thing that we need to calculate is the distance from Sandy's home to the drugstore to the vet. So I'm just going to write down the total distance from home to the drugstore to the vet, and I'm going to remind myself that we're measuring these distances in miles. So our distance from home to the drugstore, written as an improper fraction, is 8/5 miles. The distance from the drugstore to the vet, written as an improper fraction, is 18/7 miles. Now 5 and 7 are both prime numbers, so it's easy to figure out that there's no common primes to the denominators of 5 and 7. So our least common multiple, our lowest common denominator, is going to be 5 times 7, which is 35. So I need to take 8/5 and multiply it by a form of 1, because if I multiply by any other number, I won't still have 8/5. That's going to result in a denominator of 35. Since I already have the factor of 5, all I need to do is introduce a factor of 7. So I'm going to multiply 8/5 by 7 over 7. The denominator of 18/7 is missing the factor of 5. So the form of 1 I'm going to multiply 18/7 by is 5 over 5. I now have my common denominator of 35, so I'll go ahead and write one big fraction with a denominator of 35. I need to multiply my numerators and then add them. The first numerator is 8 times 7, which is 56. I need to add to that the second numerator, which is 18 times 5, which results in 90. And when I add 56 and 90, I end up with 146 over 35. Now, you might be tempted to change this to a mixed number. But remember, this isn't the last number that we're after. We're after the distance from the vet back to Sandy's house. So I don't want to change this improper fraction because I still have arithmetic that I need to perform with this number. So now what we need to do is we need to figure out the distance from the vet back to Sandy's home. And again, let's remind ourselves and the reader that we're measuring these distances in miles. So we're told that the total distance for the trip is 6 miles. We just calculated that the first 2 legs of the trip encompassed a total of 146/25 miles. So I need to subtract from this 146 over 35. 6 clearly does not have a denominator of 35, so I'm going to go ahead and write 6 as 6 over 1 and multiply by 35 over 35. And I need to subtract from that 146 over 35. I have my common denominator of 35. So all I need to do is simplify my numerators and find the difference. The first numerator is 6 times 35, which is 210. I still need to subtract the 146. 210 minus 146 is 64. So as an improper fraction, the distance from the vet to Sandy's house is 64 over 35 miles. But you know, in applied context, it actually can be useful to change the improper fraction to a mixed number. Because most people, if you told them to go, say, 5/2 miles, the first thing that they would say is, well, let's see, what is 5/2? It's 2.5. So let's save them the trouble of having to change it, and let's change it for them. 35 goes evenly into 64 only one time. And when we take 35 away from 64, we're left with 29. So 64 over 35 is the same as 1 and 29/35. Now, it would be really tempting to just stop here and say we're done with the problem. But it's too soon to stop, because anytime you're given an applied problem, you want to write a clear conclusion. And in your clear conclusion, you need to make sure you include several things. What constitutes a good conclusion? Your conclusion should always be written using a complete sentence. Your conclusion should clearly convey in words the object found as well as its value. And if units are present in the problem, then they must also be present in your conclusion. So let's go back to the problem we were just working. So far, the last thing we've written is 1 and 29/35. That does not satisfy any of the criteria for a good conclusion. The first thing we want to do is make sure we clearly convey what it is that we found. Now, I could just say distance is, but that doesn't clearly convey the distance that I found. The distance that I found is the distance from the vet office to Sandy's house. So that's the first part of a good conclusion, something that's saying very explicitly what it is that we found. And this distance is 1 and 29/35. But again, this is not complete. Is it 1 and 29/35 kilometers? Is it 1 and 29/35 feet? I need a unit here. And the unit is miles. And now we have a good conclusion. The distance from the vet's office to Sandy's house is 1 and 29/35 miles. Let's work another problem. Suppose that on Monday, the rainfall in Portland was 1.5 inches. And the following day, the rainfall was only 1/3 as much. What was the total rainfall for Monday and Tuesday? Let's again begin by pulling out the important information from this problem. On Monday, there was 1.5 inches of rain. On Tuesday, the amount of rain that fell was only 1/3 as much as fell on Monday. And the question is, what was the total amount of rain that fell? I think a good starting point here would be to calculate how much rain fell on Tuesday. So again, to help orient myself and anybody reading my work, I'm going to write a little phrase indicating what the calculation I'm doing is calculating. And what I'm going to calculate first is the amount of rain that fell on Tuesday. And I'm going to go ahead and indicate that this amount is being measured in inches. This allows me to not include the unit when I'm performing the calculation. Now I need to think about the phrase 1/3 as much. And sometimes it can help you think through phrases like that if you use kind of easy numbers, like 1/3 as much as 12. You know, what's 1/3 of 12? And I think we could all figure out that 1/3 of 12 is 4. So then you want to take that idea and consider, all right, what operation is it that I perform between 1/3 and 12 that results in 4? And the answer is multiplication. 1/3 times 12 is 4. 1/3 of 12 is 4. 1/3 as much as 12 is 4. So in order for me to figure out what's 1/3 as much as 1.5, I need to multiply 1.5 by 1/3. But it's kind of tricky to multiply a mixed number by a fraction. So before I perform this multiplication, I'm going to rewrite my mixed number, 1.5, as the improper fraction, 3/2. 1/3 as much of 3/2 is the same as 1/3 times 3/2. I can see that when I perform this multiplication, there's going to be factors of 3 in both the numerator and the denominator. And when I pull out those factors of 3, I'm going to leave behind a factor of 1 in the numerator and a factor of 2 in the denominator. 3/3 is 1, and 1 times 1/2 is 1/2. So now I'm set to calculate the total amount of rain that fell on Monday and Tuesday. The total amount of rain that fell on the 2 days, again, we're measuring in inches, is the amount that fell on Monday, which is 3/2 inches, plus the amount that fell on Tuesday, which is 1/2 inches. 3/2 and 1/2 is 4/2, and 4 divided by 2 is 2. So there was a total of 2 inches that fell on the 2 days. Now it's real tempting to think we're done with the problem, but we're not. We still need to write a complete conclusion sentence. When we begin our sentence, we want to begin it with a very explicit description of what it is we were asked to find. We were asked to find the total amount of rain that fell on Monday and Tuesday, and we calculated that that amount was 2 inches. All right, let's see one more example. Let's suppose that Carlos distributed 12 reams of paper amongst his office mates. And let's suppose further that each employee received exactly 2/3 of a ream. Here's our question. How many people is it that received paper? Now, the key to this problem is figuring out what mathematical operation needs to be performed between the numbers 12 and 2/3. And I'm going to use an idea that I suggested on the last example. I'm going to change this problem to easier numbers and see if I can get a grip on the operation that's occurring when answering the question. And the tricky number here is the 2/3 of a ream, so I'm going to change that to some simpler numbers. I'm going to ask myself, suppose there were 12 reams of paper and each employee received 2 reams. How many employees are there? Suppose there were 12 reams of paper and each employee received 3 reams. How many employees were there? Well, if there were 12 reams of paper and each employee received 2 reams, it's pretty easy to figure out that there were 6 employees. Similarly, if there were 12 reams of paper and each employee received 3 reams, it's pretty easy to figure out that there were 4 employees. So I need to now think in terms of mathematical operations. What operation did I perform between 12 and 2 that resulted in 6? That if I performed the same operation between 12 and 3, the result is 4. And you've probably figured it out that the operation is division. 12 divided by 2 is 6, and 12 divided by 3 is 4. So in both cases, what I'm doing is I'm taking 12, the number of reams of paper, and I'm dividing by the number of reams of paper that is received by each employee. There's another way I could have figured this out. It's something called unit analysis. In this problem, the knowns are the number of reams total and the number of reams received by each employee. The unknown is employees. So what I want to do is kind of pretending that these units, reams, and reams per employee are numbers. What mathematical operation could I perform between reams and the fraction reams over employee so that I ended up with employees? And again, the answer is division. If I take reams and I divide by the fraction reams over employees, this is the same as taking the fraction reams over 1 and multiplying by the reciprocal of reams over employee, which is employees over reams. And by golly, there's a common factor of reams in the numerator and denominator, so I could rewrite this as reams over reams times employees over 1. And, you know, even though reams isn't a number, if you take anything and divide it by itself, you end up with 1. And if you multiply 1 by the number of employees, you end up with a unit of employees. Any way we looked at it, the way that we got our answer was we took the total number of reams and we divided by the number of reams received by each employee. So the number of employees is going to be our 12, which is the total number of reams of paper, divided by 2/3. That's the number of reams received by each employee. we can rewrite this as 12 over 1 times the reciprocal of 2/3. The reciprocal of 2/3 is 3/2. Now, I could go ahead and factor the numerator into its primes and approach the simplification that way. Or I could just say, you know what, 12 times 3 is 36, and 36 over 2 is 18. Or I could just think 2 goes into 12 6 times, and 6 times 3 is 18. When you're performing this fraction arithmetic involving numbers, you just need to employ whatever strategy works for you and make sure that any work that you present is presented in a clear, well-documented manner. Since I can do 12 times 3, which is 36, and divide by 2 is 18 in my head, I'm just going to go ahead and write down that this is 18. But I'm not done with the problem yet, because I have not yet written a nice, clear conclusion. So I need to say that the number of employees that received paper was 18. Now, you might be looking at this sentence and thinking to yourself, boy, that's not the most beautiful sentence I've ever seen. And you're right, it's not. I could have just said that 18 employees received paper. I just was trying to kind of give you a model where your sentence structure is always the same. What is it you're looking for, and what is the result? If you wrote 18 employees received paper, that would be an A+ answer. And that is the conclusion to today's lesson.